Hi, good morning, guys, to another Advent Code, day 16. As you can see, yesterday I figured out that the second part of solution, but yeah, it was so late at night I finished that I really didn't manage to record a video about that. Mm. And by the way, my solution was very overcomplicated. It turns out that there is very simple analytic solution you can find online about that. And you can see that I already finished today's puzzle. And the reason for that is that when I read the description, I basically knew it will not be something I can do on camera. This would be too difficult to handle this way, and I will just do a solution and I will make a video explaining it. So what is the problem? The problem is that we have some graph, you can tell. So you are in some underground or some canal system, I think, and then you have some valves in this place, like they are named A or BB or CC or so, and every valve has some throughput or some rate, right? And then every valve has tunnel to another valves. Right? From AA, you can go to those valves in single step or 1 minute is how it's described. So I would talk about steps maybe, because it is the atomic time measure in this very puzzle. So you can see there is a graph. So there is a graph because from and it is, by the way, it's undirected graph. So you can go from A to D and to other places, and then you always can go back. So from A you can go to DD, from DD you can go to AA. This is I don't think it is stated in the task, but that is a case. At least it was a case in my data set, and I assume it is. So just to maybe visualize that this is a graph. Let's say this is AA, right? So it goes to DD, and because I know there is a connection, I can draw a line, right? I can draw a line to II from here to, and then I don't know, BB. Okay. Here is a line. Now going to BB, there is a line to AA and to CC, and so on. I can build up this kind of graph basic on my input. Let's maybe add another CC. CC goes to DD and BB, and we already have connection to the BB, and we have DD here, right? And I could go on, but it will take some time. From D I need to add EE, and you know, I really don't want to finish it and waste time on drawing graphs. And there is another thing, which is flow rate. So first, let's ignore flow rate for a second. So I told you that we were walking through this graph. We can go from AA to BB in a minute, right? In a time step, and we can walk through the graph basically, right? So doing this loop is 1, 2, like this loop. I mean, let's mark it. I could go this loop, and it would take me 1, 2, 3, 4 steps. But I don't want to do any loops in this task, just to visualize. And then there is water. Basically, we are drowning, and we want to release water from our place wherever we are. And every valve has its rate. For example, B here has a rate of 30 units per second, let's say, per minute. I think it's per minute, right? I don't remember what was the unit, it doesn't matter. So how does it work? if you we have a limit of 30 steps, 30 minutes in our for our solution. So for example, if we release AA, we always start at AA. This is our always starting point. This is kind of important. So if we release the AA valve, we open it at the first minute. It took us a minute. So starting second minute, we the water would flow through this valve, right? So if I would, let's say what I can do, I mean I can open AA in the after first minute. So starting from second minute, something would happen, but it's not very helpful as A happens to have 0 units per minute, and there are many valves with this 0 throughput, by the way, which would be also important. But what we can do, we can open the BB valve, and we can do it at earliest after second step, because we need one step to go there and one step to open them. So if we do so, then through the whole simulation, let's say, we would have 13 times 30 minus 2 water flowing through this valve, right? So the earliest we open the valve, the more water we can release through this valve, right? And maybe you know where it goes. The question is, having 30 minutes, how much water can you release? And first thing to realize is that this is non-polynomial problem, which means there is no polynomial solution for that. Probably, I mean, there is pretty good reward for proving that. It's not proven yet, but we are assuming that if someone finds polynomial solution to this puzzle, you could be rich with that. But anyway, jokes aside, this is non-polynomial, and I know it because, I mean, maybe I'm wrong, but I'm pretty sure this is basically the problem of which requires you to go through all possible permutations of those valves. So how the solution, the first approach, how it could go, how we try to solve it. So the easy thing is to realize that we actually gain nothing by randomly walking through this labyrinth. The only thing which is important is opening valves. This is the only thing we care. So what we can do, we can just order those valves somehow. Let's say there's order, like we can go like BB, then DD, then EE, then CC, for example, and so on. I can do some ordering, and what I can do, I can basically include every valve in my puzzle in that ordering, right? And if I want to find all the orderings, that would be all permutations of my set of my graph of my valves. All permutations of those valves are basically those orderings. And now, what this ordering means, this particular ordering means that go to valve BB and release water. Then go to DD and release water. And we always try to do it with the shortest path. Because always, if we have particular ordering, we want to open valves, then 100% you want to use always the closest path, because taking not closest path doesn't give you an advantage. But what is tempting to do is always start with the biggest throughput, right? But it is kind of a trap, because what if there are, I don't know, like 31 valves on this path up until you find this magical ZL valve, which is very interesting for you, right? I mean, every step that takes you time taking every step, and then you go back, and basically you can go here, B, release the B valve, right? And and instead, what you could do here, you could go to EE, which is, what is EE? EE is a very bad example, but let's assume EE would be like 14. Like assume that. It is not like which is in the puzzle, but so if it is bigger valve, right? So you could be tempting to go there so you can release it earlier, but instead you can just go to B and then go to C, maybe release the C, which is additional, take this closer path, and B is maybe a bit slower, but you gain it earlier, and it would release way more, or not way more, but more water in total. I'm not sure if you get this, but this is just to show you the reason why it would be not always the case. And basically it is very difficult to predict which strategy is the best, because the pathing is so important. Like, we have only 30 steps basically, and there is no way to tell that this EE would be better to go before BB or after FF. This ordering is completely it's not possible to be predicted at all. So what we have to do basically, we need to go through all the permutations and figure out which permutation is the best. And yeah, there are, in the final input here, there are how many permutations? Let me see, or how many valves? Let me get my puzzle input. It's like roughly this much. I know, 30-ish. So how many permutations are there? Like, let's say it's 30. Oh, sorry, I want different ones. It's that much, right? It's that much. So let's assume it's 30. How much is that? It's pretty much that many permutations. And bad news is that approach takes forever to calculate. But there is very simple permutation you can do. I'm sorry, I'm not showing you code, but code is actually different. I try to show you approach to reach that code for right now. So there is one single observation you can make, is that there are valves which are many valves. Most of those valves has rate 0. So we never want to release valve zeros, because it would give us exactly nothing, and it would cost us time. It would cost us some steps. So we can filter all those valves 0 out, and we can completely not include them in the permutation, and then we can do exactly what I thought, except only for non-zero valves. And there are 15 valves in the final test. So 15 how it's called in English, sorry, forgot. So if we have permutation, how many permutation of 50 element are there? Way less. It's like, before this that was 32 zeros, right now it's 12 zeros. So way less. And this would actually, if you want to do that, so we want to go through every permutation and check how how much water you would release with this permutation, that would work. I mean, I don't remember how long is the solution, but it worked. I tried this. I wait for it for some time, but solution came out. The only thing is, how do you calculate it? I mean, you can do it with some kind of fault. If you know the permutation, if the permutation is not, that's very simple, because you just takes those steps. You can even do simulation. You need to find the closest path to wherever you want to go. You subtract from your time you have left that much plus one because you need additional minutes for releasing the valve, and then you can do this trick. Instead of accumulating, calculating every single step, then you know that if you released your valve at some t or time t, so at second time frame of the second, then you can just calculate how much water would release through this valve. You don't need to increment this. You just do this. So T2 is this. TE basically is I here. This is how you accumulate this, and this is actually very, very simple to figure out, but this is how you do that. But there is another approach you can take, which is completely the same. This is completely equivalent approach, except you can think about that a bit differently. You can think about the whole problem as a game. This is my second approach, which works a bit better. So how do you do that? First, you always are in the AA place, and then you can take an action, right? What is an action? Action is going to place. We are doing exactly the same thing as before. In an AA, we have 0 points, right? What you do next? You take some action. This 0 points maybe a bit misleading. So the first action, for example, would be, we take any action here. We are building the game tree here. We take BB and we release it. And to make it even better, we already know we want to avoid nodes with 0 rate, right? So we go to BB, and we already know that at this point we would, okay, A have 0 points. Actually, those points would be nice. We have 13 times 28, because we do it second step, we can calculate the steps. So in this node, this is how many points we have, because we would release this much water. And then we would like to keep time here on this game tree, so we have 30 more seconds. Here we have 28 more seconds. Then we try to take next valve, let's say CC, because it's next on the list. And then we here CC would be available through BB. I'm right? Yeah, I am. So we need only 2 steps. So CC has flow rate of 2. I go at like 2 times 26, because this is how much time do I have. 28. And actually, better than having those values, we can actually add this. So this would be, you would add this, and with the CC node, we will keep added value here. And we go on, and we try to extend this as long as we reach some node, doesn't matter, with some points, and with such time that we cannot find another node we can go to. Or even we can say with time, okay, no, not less than 0. So we are going to, up until we find some node, so we cannot extend it further. Why we cannot extend it further? Because the node we are taking is the first node which fulfill some conditions. And the first condition is that the node has more than 0 flow. This is like light. There is some flow. This is the first condition. Second condition, it was not visited before. We need to keep some track of which node we visited. We can do it with the tree, and it should be done this way. I was lazy and I did differently, but you will see that. And the third condition is that after we go to this node, we have at least 1 second left, because we need at least, after we go to this node and open the valve, it's valve, so we need distance, previous t. I always need to figure out distance to this node, this next node, and then I need to subtract this distance from my time, then subtract one more because I need to open it, and I still have to have at least 1 second left, because if I don't have, this valve doesn't give me any points, right? So this is how I choose valves to open. And if I cannot add any more valves, then I finish this, and this is my maximum points. I keep this as max points, right? And then I am backtracking. So what does it mean? Then I go one step higher, and I am trying any valve which is farther than the ZZ and fulfills my another conditions which has to fulfill, like another valve. So when I would backtrace, you know, beyond the C, okay, I'm backtracing through this. Okay, so I probably took DD here, but I'm backtracing up, and I am on DD node. So I am adding DD node here. DD has positive flow rate, and now can I go, how far is from BB to DD? From BB to DD, I need 2 steps because I need to go to A. So I would have here like 20, which is flow rate, times 24, because 28 is here. Sorry, 25. And why 25? Here I had 28 after this one. I need 2 timestamps to go there, because this is distance, which is 26, and I need 1 second for 1 minute to open the valve, which is 25. So, and then I have this and 25, and then I go build my tree. And you can notice that this is exactly the same thing I told you before, except I added you this information, how you can build all the possible permutations. And this would, I think this would give an answer in some time. I don't know if reasonable, but there is one very simple optimization you can add. I mean, there are 2, but I didn't figure out you can cache. So we don't have caching in my solution. It is killing me. Sorry. It should be Dima. Okay. So what you can do is caching, which I didn't do, and what you can do is alpha beta pruning. How alpha beta pruning works? For example, here you can go. You are backtracing, and you backtraced to BB up from here, and your max is some 80. Let's say this is something I figured out right at this point. Oh, I'm drawing all the time and giving you wrong screen. So this is what I wrote. So you are going down, right, and then you are backtracing and choosing another path, right? Sorry for not having a proper screen. So you can try to now think about this. Yeah, I'm going down to backtrace to build my tree. I backtrace, I go down. Here I backtrace. This is my 25 based on my previous value, right? I need to using that. Anyway, now what do I do next? I do alpha beta pruning. So how it works, at this point I am taking this DD, but before I take this DD, I can estimate how much points I can even get going there. So I can do this by taking, okay, DD can give me this many points. So I can accumulate this points plus this points. This is how much points I can get going this path. Plus, I can assume I would open all my valves instantly, right now. What would happen? Because if at this point, if I open my valves in next step, or even right now for simplicity, and the accumulated flow plus what I have here will not exceed, will never be more than my maximum, then no matter what, I cannot get my maximum through this path. I'm already wasted too much time. And alpha beta pruning actually gave me a significant boost here. And now let's go to the code. Where's my cursor? Sorry. Go to the code and see the solution to the first task. Couple things happened, or many things happened. First of all, we have our input, and I am reading it to some hash map. String is my name of my valve. Then here is flow of my valve, and there are destinations of my valves. So I am doing exactly the same what I did yesterday. I will not go into that too much. I just did some smart strip prefixes and so on. And then what I did, I pre-process input, and why is that? So hash map has this constant time access, so I can access my hash map technically fast, right? Because I just need to hash something, but for every time I access hash map, I need to hash it, and hashing is actually kind of expensive, and I know I would access this map very, very often. So my first instinct was, I want to pre-process it. So instead of having this this big hash map of string to some information, I would have a vector of flow and tunnels. And what is tunnels? Tunnels is exactly the same as what before, except instead of being vector of strings, it's vector of indices where I can go. So now it is very similar interface to my hash map, except I am indexing with my integers, which is far more efficient because I don't need to hash, because it's way more local and so on. How do I do that? I collect my keys. I sort them. Why did I sort them? To make the look easier, because now if I sorted my keys, I can do binary search instead of linear search. I don't know if it was good choice, but I did it instantly. And then what I did, I went through input and I just changed. I assume those would be my keys positions, and I have this fold here. Fold is, what is the first thing? The first thing is I am folding. Oh, this vector is a state. Yeah. So this is vector of zero empty smart. Yeah. So I assume there are len entries there, right? And I start with saying that there are no paths from this node, and there is no flow at this point. So this is kind of initial vector value. It is done to not struggle with any, I just want to be able to assign to some particular index in this vector, so I want them to be already there. So I calculate the key, the index of the, I look for the index of my key, then I just map the tunnel mapping, looking for proper places, and to the proper to the index of my key, I just assign new value. So this is how I process this, but this is not the whole preprocessing. Then I build my distance table because I know I will often try to find the shortest path. And finding the shortest path is, as we saw, I think, yes, 2 days ago, it is not a trivial task to have. So what I did, I created this not huge, but this big matrix where here I have like AA, BB, C, DD, and so on. AA, BB, CC, DD, and so on. So those distances are obviously 0 because I can, and this is not this important, except this may be relevant, but it's not in our solution. But doesn't matter. What matters is that from AA to BB there is distance of 1, A to DD is distance of 1. This is how my array starts. I don't remember it, but let's say DD to CC. DD to CC, let's say this is also 1. Let's say I don't say it is. Let's say. So then you can build it up. So for example, having that, you can go to CC from AA from through DD. So this would be 2 in such a case, right? A to CC is 2. BB to CC. From BB you need to go through AA and DD, so this would be 3. This is how you build this kind of stuff. DD to BB, this is 2, I think, something like this. Okay, those are those series. And this is what is called distance table. And how do we build that? We do what we did when we were pathfinding. We do what's called either Dijkstra. Did I do Dijkstra? Or yeah, I did Dijkstra for that. But a bit modified because we are not looking for this path to somewhere. We just want the whole map to be populated. So I created this distance table. As you can see, I used a single chunk of memory instead of vector of vectors. This is a bit more efficient, like a bit. And I am used to this pattern. I have my binary heap. And then, first of all, for sure I need my initialize this array to maxes, but I already know that the shortest paths on the diagonals are 0, so I can basically fill those. So I would know early exit in many places. And what I do I initialize binary heap? Why didn't I initialize binary heap? Oh, I do, but to build the full distance array, I need to basically start from every node, like to be sure that it is properly built, because I need all the distances between nodes, right? I could probably make it twice as fast by reducing it a bit, but it doesn't matter. What do I do? First, I need to initialize the first binary heap, adding all the tuners to it with the first of all, I set distance to all the initial tunnels, basically. To all the tunnels I can direct to 1 in my row. So this is my row times false plus tunnel where I am going, and basically it is always symmetrical. So I could do here tunnel idx, and then I could probably reduce, yeah, having that I would reduce this lookup later, but it doesn't matter. right now this is true. And what do I do now? I add all my students I can reach to my priority queue. To my binary heap is basically priority queue with the weight of 1. I mean, they are always sorted, so the first position is tuple is how to sort, right? And tunnel is the tunnel index, next tunnel index. And then as long as queue is not empty, I just take next tunnel. Next tunnel, and I have distance to it. I take all the tunnels I can reach from this point, right? Input tunnels. I completely ignore the rate for now because I don't care about this. And then I go through all every tunnel. I calculate distance. I am checking distance to this tunnel. Wait a second. I am checking if already calculated distance from my initial index, because I'm working on the initial index right now, is bigger than the path I just reached it through. So distance is here. So distance is how I reached the previous tunnel, right? Previous node. And I need to add 1. If it is bigger, then I have closer path, and I am setting the new value of the path, and I need to recalculate the whole node because it reaches some other nodes with possibly closer path. And I do it for every source index to populate it for every row of my distance table, and I return the distance table, and it would make, I mean, I will have calculating distance in constant time. I will not need to do any kind of path searching later. Oh, do I use this next permutation? I think this is unused. Why is it used? Is it not warned as unused? Let's ignore this. This is stolen from Stack Overflow, because as I told you before, I considered the permutation solution and I was too lazy to implement the next permutation function. It is basically re-implementation of next permutation function from C++. And it's kind of easy to understand, but I will not go through this because it's not part of my solution. So part 1 solution finally. First of all, I created this constant because I was not sure if it would be some changes when I was implementing, and yeah, I did my time as a constant. It's always helpful. And what is this? This count is size of my input, and I use it because I would index my distance table with formula like from times count plus 2. This is how I calculate index for my distance table. I could do it somewhere else. I will. This solution is, by the way, very dirty. I spent too much time on it, and I just wanted to understand what I'm doing. I was doing it very slowly. I don't like the code. It could be improved, but you know, it's difficult puzzle. So let's try to go through this. And now my valves. And what I do here is I collect all my, I am going through all my input, and this would be also done for part 2, but I enumerate them, as you can see. So I have the original index of the valve and the rate of this valve, because I want to collect them to this vector index rate. And I want to filter out any valve which has no rate, because I don't want to include it in my solution. So I just created this valves searching vector here. And what I do here, I sort it. And now I think I did it very badly, because I think that what I forgot is that after sort and maybe this would even make it faster. Let me quickly see. Did I do the same for the part 2? Did I forget to? Let me just quickly run this. If it would be any faster. No, it's not much faster. Okay. So I didn't screw up. I think doesn't matter. So let's get it back. I sorted it via rate. Which I think I should not do. My idea here was that it is kind of intuitive that taking the valve with the bigger rate would be generally better. It would be sometimes worse, but it is somewhat heuristic we could follow, and I wanted to follow it this way. This way, like taking the bigger rate first. But it doesn't matter. I mean, I'm 100% sure that you can remove this line. I am not sure if it would be less or more efficient. Doesn't matter. And here is how I keep my information which valves are released. So I have vector of which is as many entries as my valves, and here is my my valves. So I just keep information if the valve on this index was already released. So that's easy. It's not any of them. None of them are released at the very beginning. And then there is my stack, because the solution for that is actually recursive. The thing is, I don't like recursion. And why I don't like recursion? Because you can eat your stack, and your stack is very limited. The thing is that the recursive solution will be way easier, because you will not need to fake the solution, the recursion. It would be faster, because access to stack is faster than access to heap. And it would be not a problem, because you have only 15 depth of calling tree, because you have only 15 valves you are considering. So this is better to be done by recursion, but I don't like recursion so much that I didn't think about that, and I went with fake recursion. What do I mean by fake recursion? Instead of just recursively calling your function, you keep your stack, which are your variables which you would like to keep your previous versions of, right? So those you cannot basically recalculate easily. And here is my valve index. So the valve I just opened. I keep accumulated flow, which I don't have to, but I keep accumulated flows for my points, basically. And how much time I have left. Both of those could be physically calculated, but I was very inconsistent with my solution here. Here is the best score I reached. And here is stat from, which is a utility. You will see how I use it. Basically, I use it for backtracing. So whenever I try to pick the next valve to reach, if I just backtraced, then I am not calculating. I am not calculating my. I'm not looking for my valves from all the valves. I need to take a valve after the previously backtraced one, right? So I have the start for that. And this is loop inside the loop, which is already you know, not too good, but I need this. So why I need this? The first loop, this internal one, is building the biggest path you can build, taking always the first possible valve, right? And the second loop is a backtrace loop. So this loop builds you a longest path. Then I check how much points are on on this path, if the last node of the path would contain this on the stack on this point would contain the flow of the solution. This unwrap or doesn't matter here, I think. And if it is better than best, then I store it on best, right? And then I backtrack once, so I take my valve out of my stack. This is the new syntax which is introduced by recently. So it is if you cannot destructure into that, go into this, and then I break, because if I have nothing to backtrace, then I went through all the paths. Here I backtrace. So if I backtrace, I need to mark my valve being not visited, and then I want my searching to start from valve +1 for next time. And now let's go through this loop, which is the core of the solution. So what do I do? First, I am looking at the tip of the stack, so the last position. And what I do, I map my valves, so it, instead of containing index of the valve, it would contain the index of the valve, but on the input. I will need this because I need this. I mean, I need this because of distance table, basically, right? This is why I need it, because distance table is using the big indexing, right? I keep my flow and time for now because I need to subtract from time and I need to add to on flow. And then I try to find a valve. What is it? This big thing doing? It is trying to find a valve which is fulfilling my predicate. Predicate is it's not yet visited. I have time for it, and I think that's all. And yeah, and for my heuristic is true, so, and my alpha beta pruning is true. So the third thing is that potentially I can go best. If I would release all the other valves, I can go best. Yeah, this is the one. So what I do, I just iterate through my valves. I want to have the indices because why I do need indices? Because I need to know which valve mark as visited, because my visited is using the same as indexing as valves. It would be easier if I would just make visited a bit longer, but I made it harder for myself. Doesn't matter. Now, I start from valves, because I know that if start from is bigger than 0, then I just backtraced. I would reset it at the very end of this. And this is very bad habit. I just did this hack because I wanted my solution and I was debugging for too long. So what do? I calculate my distance. I do find map. What find map does, if it returns a sum, it would return it is like find, except find would return you exactly the found item. Here you can immediately map it, right? So this is what it does. So first I need to calculate my distance. And now if the valve is already released or distance is bigger than my time, then I return null immediately. I'm not sure if I couldn't make it even better. Bigger or equal. If it's equal, it has to be at least one more. My time has to be at least one more than distance. So yeah, this is okay. Even probably +1 make it even faster, because I need at least one more additional minute of flow. I found this +1 here. Yeah, this +1 has to be I will not modify it. I'm pretty sure it would work, but those are minor improvements. I don't want to destroy my solution because of this kind of things. My time, I need to reduce my time by this -1, right? And what do I do now? I just calculate theoretical maximum flow if I release everything at the single step. So this is basically, I enumerate, I try to filter map. I filter map them by the fact if they are released, and if they are not released, then I return its rate. I sum the rates and I multiply it with by time left. And I add the flow I already accumulated. If max flow is better than best, this is not, don't even think about this valve, this node, because we will never get best. And what I do now, if I accept the particular valve, I just add my next flow and I return which valve I chose, what is my valve and the flow, and how much time have I left. I mark my valve as released, and then I push my new game state to the stack, and I reset my stuff. And this is solution for part 1. And then we are going into part 2. And part 2 is exactly the same, except you have less time, 26 minutes, which is fine because you have bigger limit. You can do less stuff, you will do it faster. Except you have your elephant helping you. You used your 4 minutes to teach elephant, and we are very happy that we can help only one elephant, because if we have more elephants and we would need to figure out if it's even worth to maybe teach another elephant, which would take 4 minutes to help us, that would be even more difficult solution. And hopefully it's not the case. We have one elephant, we lost 4 minutes teaching him, and we would need to figure out how much we can release. And by teaching elephant, it means we just told him which valve he has to open. We assumed we have our solution, and we want to figure out how fast we can go. So how do we do that? Probably it is the same thing, except let's think about our approach. So this is still the same game, except every action we take is not picking another valve, is picking another. There are two actions, two categories of action we can have. We can pick another valve, or our elephant can pick another valve, right? Because every valve can be picked by only one of us, and it is not clear if it's best to pick it for a valve to be picked by elephant or us, because it is dependent on not only how much time we have left, but also how where we are on the graph. So this is kind of complicated. So let's create this whole thing. How we model our graph right now. I added the root node, which gives the initial state. So initial state is where we are, on which valve we are, on 0, or rather it's not even 0, it's AA index. We are on some valve AA, elephant is on valve AA, then I keep points or flow, and how much, so sorry, on the very beginning points is always 0. So here I keep how many points do we have, then I keep how many time did I have, do I have left, how many time my elephant have left, and how many, what more do I keep, how many, do I need to force next move? So let's call it for, which is 0 at the very beginning, and which valve did I add it for beginning at 0. So I will go to the false and to this last thing in a second. But basically right now we can ignore this, we can ignore this because we can infer this from the game. I want to just call the moves easily. Let's ignore this and this. So let's say that this node is us taking the node BB, right? So this state would be BB AA. And then we are taking node DD. And elephant is still taking, and if we chose that elephant should take some node, we demark it as DD because we didn't change my state. So we built a tree like that. And this is a shame because now instead of having 15 permutations of 15 elements, this is permutation of 30 elements, basically. Because of the fact that every action is not only the action is not only valve to choose, but it is also who chooses. It's a bit less because we can pick only 15 elements and not every element we can pick, but it's at least much. Sorry, I am too lazy to even calculate the exact number. But this is basically what we try to do here. So we try to build this kind of tree and figure out what is the sum we can get here, right? And this is the same solution basically because the core idea is similar, but there are a couple of changes. This is exactly the same, I think. Yeah, solved by key. This is disaster. I decided instead of keeping here in the valves before, I kept index and rate. I decided to keep only index to make some stuff a bit easier to index. And then you see my state is this fourth and this added value, which fourth is both are used for backtracing. So let's go to the solution. I push my initial state, and yeah, this is important. Before here I was using index in my valves array, right? And it caused me so much problems in calculations later, so I decided I will keep only the index to my input array because I need it for my distance table. Basically what I should do, I should reduce this input base to only keeping rates or something. I don't need this tunnels anymore, and this also makes it a bit more clunky, but doesn't matter. So oh, we went to part 1, sorry. Part 2. So now I keep indexes to distance table. So because of that, I needed this added value. So on backtrace, I basically know which var to release, because I still want to have the released array not even be an array. Right now I figured out that I have only 15 valves, and I can just use my U32. I could even use U16, which doesn't matter at all performance wise. It is completely the same because of how CPU is working with that. And this is basically bit flag. and it turns out it makes my solution from 2 minutes to 1.5. So it was significant improvement, changing this vector of bulls to bitflags. And yeah, this fault is something I would really explain in a second. This is the same force as this force, by the way. I put my initial state. Those two doesn't matter for the initial state. So 0 best is the same what was here, and false. Okay, we are on false. So it may happen that we will do exactly the same thing. We will try to get the next possible valve, and then we need to decide if elephant or if we are taking this. So I assume that it's better to give it to the one who has more time. So this is what I do, but on backtracing I always need to check the other option, and this is force. So is force if 0 is 0, it means it was not reached by backtracing. Use the better pick, basically. 1 means elephant was checked, try with yourself. 2 means you tried this to take this valve, but maybe it's better to give it to the elephant. This is what the force is. It should be done differently. I know it should be done differently, but it is the easy way to write it. Maybe not to understand it, but to write it. And then there is the same loop as it was before, except I need to take out more stuff. And this next force is basically I set it to 0. If I added it after backtracing, then it's 0 because yeah, I don't care. And added is whatever I just added, right? And also next force is set in backtracing to 1 or 2 depending on who we backtrace from. The same find map as before. I calculate both distances, and this early cut is least end to by index. This is how I just check if it is released. This is just bit operation, and here at least one of us have more time, any time to spend. If we have no time both, then we don't go with this, with basically any option. And force. Now force is relevant only if we are taking exactly the same position we backtraced to. So if we just backtrace from D, we can try D again with another player. And this is the only case we care about force. So only if index we are considering is equal to start from the first index. And now there is this funny match where I try to figure out who do we pick, and basically basic on who would take the valve, we set next valve for as an elephant, next time for as an elephant. This is the time we would use to calculate the points, and we figure out who we will force next, and we match it based on force. If the move is not forced, the choice is not forced, then I pick whoever has more time. And if I have more time, then I take a valve. My time is my calculated next time, and my time is used to calculate the thing. And then next move with this node would be tried by elephant. That's why the force is 2. This is symmetrical, but I pick elephant, and here 1, and but I take 1 only if I mean I take the valve only if I have time, right? If I have time after taking it. If it's a case, then yeah, we are going there and we do not backtrace. We don't backtrace. I mean, we don't force anyone at all. We want to start from the next because we checked both players. And same for forcing elephant. This would be taken if the chose was forced, but we have no time. Then we will just say, okay, you check this already. Calculating flow, it is easy because we know the time we want to use. And this is basically collecting valves which are not yet released. I sort them to have kind of precise estimation how much I can release. I do this by assuming I would unlock them in the exact order of from biggest to lowest rate, and I would always have one step to reach them. So this is basically the most optimistic situation I can find of the plane, and always I would use the guy with more time, because if I can always reach it with one step, it would be for sure the best way to do that. So this is technically the best flow I can achieve. I do this because it really, I mean, having better heuristic here just improved time more. But I don't think it was the most important improvement, but maybe it was actually, which made my time to minute and a half. It's still minute and a half. It's too slow. Yeah, I cut the branch off if I cannot get this much flow, and yeah, this is basically exactly the same. I just modified the backtracing a bit. So first of all, I don't backtrace if there is only a root node. In this case, I don't want to backtrace because it won't work. This won't work because the root node doesn't follow the next force and added principles, and yeah. Also, the first node is something we have to start. We cannot start anywhere else, right? Then, I mean, this break would never happen because we would break here always. But yeah, we could unlock probably on this pop. And I need to know if I force next after this backtrack and which one I added. I need to know which one I added because I need to unrelease it. And I need to set the force. If I need to force my next move, then I need to repeat my last move with the forced option. If I don't force my next move, I go with whatever was added +1. And this is the solution for part 2, which is basically building the game tree. And if you are curious how to improve on that, caching. Because what you can do, while backtracing, you can keep information of how much points you can possibly get at the best situation from this point, because you can, when you backtrace, you already took all the possible paths from this point, which were even to be considered. So if you took all of these paths, you can take the best of those paths, and this is how many points you can get going into this path. And why it is relevant is that you can figure out that there are some states that would always be the same, kind of. So for example, if you did the different game order, but you ended up with the exactly same valves released, and you are on the same spot, and elephant is on the same spot, and you have the same amount of time, and your elephant has the same amount of time, right? Then for sure, 100% sure, you can have you can have exactly the same points since now, if that makes sense. And you can go even better if exactly same valves are opened and you have exact position of points, I think, or maybe not. I don't want to go into that, sorry for that. But this is how you can cache it. So if you are in the same position, elephant is the same position, no matter what path you took to reach this, because maybe swapping to vars didn't change the result so much, or maybe even to change the result of how much points it changed the result in terms of how much points you get till now, till getting there, but you cannot get more resource since now. So you can be sure how much points you can get since now, right? If that makes sense. And you can cache this information on backtracing. And now if you find yourself here that you have exact position which was already cached, then you don't need to even build this node, because you can exactly know how much more points you can get from this point, and you can add to your flow. And if it's more than best, then you just update your best, because it's not heuristic, this is exact value. And if it says, then you can ignore this. And I would like to add cache, but I'm lazy and it's late, so I will not. But maybe you want to try. Okay, thank you. I know it was long and it was not even implementation, it was just walkthrough. Sorry for puzzles to be more difficult, and sorry for avoiding obvious solutions which would be better. And by the way, I know for the fact that I watched YouTube already. Solution with cache is faster than solution with alpha beta pruning, and I suspect that solution with cache and alpha beta pruning is even better. But yeah, see ya tomorrow. Bye.